The topic for the next couple times, and then we'll be coming back to these because they're so important, are classifying spaces. And I take a bit of a topologist view of pedagogy in general. I mean, I guess if you have a hammer, then you tend to see the world as a bunch of nails, or at least some parts of the world of nails. So, you know, I think it's important when you're studying classifying spaces to know about the simplicial model. And that's closely related to the nerve of a category. Also to just understand what's so important about the homotopy type. And what I'm going to do for just a moment is, well, no, I'll keep that at that. And then finally, we'll also think about various important natural, as in nature, geometric models. And as I said, as a topologist, I somehow think that the work that we're doing is maybe filling in a simplex, sort of connecting these, or maybe it's higher dimensional, although perhaps I should really think in terms of being an algebraic geometer, and there's some sort of generic point of classifying space here, and it specializes to these different viewpoints. So maybe I was mistrained. In any case, let's start with a simplicial model is where I've chosen. So again, the problem with any pedagogy is then time is linear. I think pedagogy is not really, but it's constrained by that. So I wanted to start with a simplicial model. And you can just sort of pretend that we as topologists feel like group elements are getting short shrift, especially in finite or discrete groups. And that what we want to do is take a group. So it can be topological, but think finite, even discrete, and take an interval and look at times on the interval, each labeled by elements of the group. And so what we're allowing the group to do is now, you know, these group elements have neighbors. And this is going to be our model for B delta G. And it's, but it's got some relations. Oh, and let me make sure I'm monitoring the chat as well. My apologies. There we go. Good. It's got some relations, namely, and I'll say them, I'll formalize all of this in a moment. Oh, and sorry, I need to get rid of this line. Namely that if I have, the main one is if these ended up overlapping, but in some way, like what I want to say is if I have a point labeled by GI and a point labeled by GI plus 1, and those crash together, then in the limit, I multiply. So we're using the group structure there. That's one relation. Another is that that the identity element actually doesn't matter. Namely, if one of these points is labeled by the identity element, then, well, the identity element just gets to come and go as it wishes in this, as we let our group elements graze. It's not really constrained. It can pop in or vanish at any time. And then the final relation is that if we, there are other places, there are special places where things can vanish. Namely, I can imagine something coming off. Once it hits the end, it just vanishes. So G, maybe this is the G1, and this is the G2, and then you just only have G2 left if G1 hits the end. So that's just a fairly concrete game you can play with elements of your group. This seems like a little bit too soon for me to go down, so I'm going to continue. At some point, I'll try to remember to go and go up. That'll make my life easier. So how do you formalize this? Well, this B delta G is, I start with a huge disjoint union of an in simplex cross the Cartesian product with the group to itself. So if the group is discrete, this is got many, many components. But then I'm going to put some equivalence relations on this. And namely, they're going to correspond to those three. So if I've got a list of times, and I'm going to always write them as T1 less than or equal to T2. So I'm using the increasing sequence of times model for the simplex, as opposed to, there's really at least two wonderful models for the simplex, and it's fun. Sometimes you need to go between them, but this will be the increasing times, so that, for example, a 2 simplex naturally looks like this. I've got T1 and T2 are the natural coordinates, and T1 is less than or equal to T2. And then I've got my list of times. And in that first really fun equivalence relation, what can happen is if I have any Ti equals Ti plus 1, then that's going to be equivalent to what I get when I eliminate one of them, but it's going to be paired with what I get when I take the group elements, and then I have the Gi minus 1 as before, and Gi and Gi plus 1 are multiplied. So that's the first relation. I'll show it all there. So that formalizes that, and you can see this kind of treatment. It's very standard. I learned this from, I think it was maybe even still a preprint at the time of Denman Milgram's group homology book. So that's what it means for when two group elements come together in the interval, they multiply. The second identification, it says that if I've got an identity element, it can be ignored. And what we say there is if Gi equals E, then what I can do is just drop the ith time, going to drop that ith element of the group. So that's how you have some formal mathematics that says that that element can come and go as it wishes. And then finally, if you have, for example, 0 equals T1, and I have my list of elements, I can drop that from the list. The first element in my, this is going to be identified with a simplex with lower dimension. The list of coordinates is the same with T1 omitted, so it's got one less coordinate, and then G1 just gets omitted as well. Great. So there's our, there's in explicit coordinates what BG is. Okay, so let's, let me now move over. And move over here. Let's start with a little example. If G is a cyclic group of order 2, then there's a unique simplex representative, or these quotients yield a CW complex. So we can talk about cells. So there is a unique in cell after identification. So even though before identifications you have 2 to the in cells, namely, I've got the non-trivial element repeated some number of times. And let's just think about how this goes. Let's think about the boundary of the cell with 2. So what are ways that it attaches to cells of lower dimensions? Well, I can, one of these could run off, say the first, and then I get the cell. And what I mean by this cell, this is a 2-dimensional cell parameterized by where both of those elements of G can occur. And this is a 1-dimensional cell on the right, parameterized by where the elements of G can occur. That single element of G can occur. So, and again, if we want, we can say, well, we have the other G was here, or I get the same thing again if I think about having the 1G hanging out on the right, again up to identification, then it disappears. And then if you think about it, I get something that where the 2 meet, but this is the identity. So really this is degenerate. So in fact, the picture you get would be a cell structure like this. So this is our G. G. I almost wrote G bar G. This is the bar construction, but a different bar construction than before. And then this is well, this is basically E, but then that's contracted. So this is a degenerate cell. And you see something that in that case is homeomorphic to RP2 for the 2 skeleton. In general, the in skeleton you can check is homotopy equivalent to RPN. I don't know if it's homeomorphic or not, actually. And in the end, this what we do know for sure from various points of view is that this B delta for the cyclic group of order 2 is homotopy equivalent to RP infinity. So, so you have these elements of the group running around, but in some cases, well, the first case that you should always start with in equivariant topology, at least in my opinion, is you get something familiar back from this this game. So, so that's one point of view, a very concrete, simplicial point of view. What I want to say next is that I'll have to move right a bit. So next I want to talk about why. So and well, the fact is that, well, BG or B delta G, so with mild hypotheses on X, the homotopy classes of maps from X to this BG are canonically in one-to-one correspondence with what are called principal G bundles over X. And what do we mean by that? What are these? These are fiber bundles over X. Whose fiber has G as a structure group. So let me give my intended first definition first. These are locally trivial free G spaces P such that the quotient is X. And then those are fiber bundles over X whose structure group is G. So you're okay in a first setting, really think of these as free G spaces. So somehow this says that if I care about free G actions, X is occurring as a quotient of a free G action, it suffices to think about homotopy classes of maps from X into BG. And well, this is algebraic topology. Homotopy classes of maps is something that you can start saying things about, say, with Hopf invariance like last time. So this BG has the following homotopy characterization. Namely, that if so if say EG to BG is any principal G bundle with the special thing about this with EG contractible, then if I have two such well, so sorry, I'm going to get characterization that then maps from X to BG classifies principal G bundles, and moreover, any other such, and this is you can say this is equivalent, but I'll any other B prime G to B prime G with E prime G contractible yields a homotopy equivalent BG. So let me, before I prove some of these for you or simply sketch the proofs, let me talk about some examples. This is our second really distinct way to think about BG. We had a concrete simplicial way. Now we have this sort of characterization of the homotopy type, but it can also be concrete in some examples. The first one, sorry. First example, again, should be G equals C2. We saw that with the simplicial model. Well, what you have to do is find something that C2 acts on freely, yielding a principal bundle. And and that's contractible. Well, C2 acts on Sn via antipodal. And Sn isn't contractible, but it's closer and closer, in a sense, like the calculus of functors sense, actually, to being so. And so, in fact, S infinity is contractible. My favorite way to think about that is that the equator of any sphere is homotopic to a null map inside that sphere. And S infinity, you can play this kind of Hilbert hotel game with coordinates and rotations to realize the identity map from S infinity to itself as homotopic to its inclusion in itself as the equator. And then at that point, it's null. So, so that means the BC2 is going to be this S infinity mod C2, but this quotient of the sphere is, of course, RPN, or in this limit, RP infinity. So we see that example again. Other example that everybody should see, quite familiar. If G is just a group of integers under addition, then perfectly fine EG is R. That's a nice contractible space. G is a subgroup of R, so it acts on R by translation. And we see that BG is S1. But if you're paying close attention, I was saying that all these are homotopy equivalent. And again, you'll see at least a sketch of proof of that. So, so that is so. This space that we started with points labeled by integers, etc. And this is infinite dimensional on the left side. This is B delta S1 is homotopy, sorry, B delta Z is homotopy equivalent to S1, which is kind of remarkable. And I'll actually say I would love to have somebody find a proof that's more direct than the one that's implied by what I do. I mean, there's an obvious map that, you know, T in S1, if I think of this as 0, 1 modulo the endpoints, T can go to the following point in the simplicial BZ, namely at time T, I'll just put a 1. So as T goes from 0 to 1, this point is going to go across the interval. And I claim that that's the equivalence. But again, this is one of the simplest topological spaces you can imagine on the left. And we've got this large simplicial thing on the right. And yeah, so homework. Since this is a geometric approach to algebraic topology mini course, so to speak, can we get a direct geometric proof? I've never found one. Great. Let's give a couple more examples. And we're going to come back to many others, so don't think I'm trying to be exhaustive here. For example, I won't spoil it, but I'll just say for symmetric groups, configuration spaces arise as examples. So that's part of my love for both of those, that they're so intimately tied. The fundamental group of any surface acts on the universal cover of the surface, which, if the surface is not a sphere, is R2. So so that implies that the surface is a B for its pi1. So some of these are familiar, but for the most part, they end up being infinite dimensional. Another key example is that the circle also acts, well, the way I like to think of this is acts on Sn, but then inside there you've got 2n minus 1. And that's a free action. And once again, as we said, S infinity is contractible. So that implies that S infinity mod S1 is BS1, but that's our friend CP infinity. And those are more typical, RP infinity and CP infinity. Most of these tend to be infinite dimensional, not all, but for the most part, they are. Okay, I'm going to prove some things, but what I'm going to do is switch whiteboards. And that will make it easier to save things in the end. So let's talk about the sketch of proof of the classification theorem and the homotopy characterization. I guess I stated them as one thing, but I'll write them as two. So again, this will be very brief, but if I have one of these free G actions with quotient X, and again, think about Sn over Rpn, that kind of thing is a principal C2 bundle. And then I want to classify those up to isomorphism. The first thing you show is that's the same as maps from the G maps from P into EG. That basically, up to isomorphism, once I fix an isomorphism type, there's a unique homotopy class of maps from P into EG that, and that's pretty straightforward because, again, EG is contractible. If you often put yourself in some setting where you can argue cell by cell and see that there's sort of no obstruction both to constructing a map to EG and then finding any such two are homotopic. And then, well, if I have a map from P to EG, which is fixed by G, then I can pass to the maps. That's equivalent with respect to G. I can pass to the quotient maps, which is maps from X to BG. And again, I'm redundant here, but for those who aren't familiar with square brackets, that's what we mean when we say up to homotopy is homotopy classes of maps between them. So this BG represents this functor of which is asking, okay, how can this space occur as some quotient of a free G action? So start with a space with some symmetry characterized by G. When I take a quotient, how many different ways can I realize a space X in that way? So then the other thing I wanted to say, and one could use this then to prove the homotopy characterization, but let me give a slightly different proof of that homotopy uniqueness. That's really what I should think about. Namely, let's suppose I do have two such. So this again will be a sketch. So suppose we have both an EG and an EG prime, which quotient to BG and BG prime. Well, I'm just going to compare them. I'm going to take the product, and lo and behold, wait, they're both contractible, so the product is contractible. They both have a free G action, so the product diagonally has a free G action. And I'm going to use this to compare. I can just project onto the first factor or project onto the second factor. If I quotient, so this is the universal principal G bundle here. This is supposed to be another, oops, another such. And what I can do is this also ends up being another such. Oh, I've got a question. Right, so I'm thinking about based maps or and or path connected spaces. Sorry, I've been neglecting connectivity hypotheses. Let me once again erase this for now. So, so we have maps like this. And these commute, since these are just quotient maps and identifying the orbits of single points. And well, since these are contractible spaces, these are equivalences. Since these are identities, these are equivalences. And so we can deduce with a little care with base points, etc. Well, so we're going to use that. So we can deduce essentially by a 5 lemma that these are equivalences, and thus BG and BG prime are equivalences. So in fact, we can see that pi I through this exact sequence of BG is isomorphic. Pi plus 1 of BG is isomorphic to pi 1 of G. This you need it at the end of this exact sequence to understand pi 1 of everybody as all G. And note that these are connected. Good. So so yeah, let me repeat everybody's homework assignment. Through this circle of ideas, well, one more. Through the next I'm going to establish that the first BG I wrote down really is a BG from this perspective, but then you have to, yeah, and then it will follow that those two models for BZ, the simplicial one with the points labeled by integers roaming the interval versus S1, those are homotopy equivalent. So, so yeah, so let's tackle that last. Why is this particular BG, from our point of view, a BG? And again, let's think discrete now for the moment. And what I claim is, and we'll be brief because part of these lectures are just inviting folks to further some further topics. Almost by definition, this BG is what's called the nerve of a category CG. Okay, I'll explain what these are in a second. So, in general, the the nerve of some category C is the realization of a simplicial set built out of that category whose insimplices are incomposable morphisms, one after the other. So they have to, there's an ordering. And then the face and degeneracies are defined by either inserting, well, faces by composing, and degeneracies are by inserting identities. And since I carefully went through the simplicial definition of BG, again, I'm going to just sort of think of this as an invitation to read elsewhere if you haven't seen this already. But you've got some kind of morphisms. You've got your objects in your category, and maybe your morphisms go to themselves, go from objects to themselves. And what I do to form the nerve is each of these has some sort of length, if I will. So this actually goes, if I think of this as length T2, this is happening between times, quote unquote, T1 and T1 plus T2, et cetera. And in that way, I've got the insimplex crossed with the sets of incomposable morphisms, and then you can imagine the identifications based on that. And then the point is that in this case, CG, well, has one object. I could call it little o for object, and then a morphism for each element of the group. And then they compose via, in the category way, via the way groups multiply. So, if you unravel these definitions, you see that the original simplicial BG is really is given by the, well, I guess there's a little translation from thinking about the G's in between versus the G's labeling points, but it's pretty straightforward. And in this language, now let me give you the EG. It's going to be a nerve of something which I'll just call CG tilde. And its objects are G. So this is why I want to think in terms of discrete for the moment, finite even. There's a unique morphism between any two objects. And we're going to think of this as Gj, Gi inverse, which when I multiply by Gi, I'm going to get Gj. So the picture of this category is I've just got the elements of the group and just unique. I've got the identity. That's the only morphism from any object to itself. And then you can check that that you can quotient this category. So I'll put it in quotes, but and the nerve. Actually, I think that is, I think I set that up to be true. So again, this means just quotient by the group action here. And why is this contractible? Well, what you can then see is any collection of simplices, and thus any cycle. So maybe there's a little bit of a pi1 calculation that we'll need. But any collection of simplices sits inside some simplex of large enough, some simplex in this nerve itself. And so that certainly pretty quickly gives that it's got no homology. So, yeah, so these are our lovely spaces. And again, if you trace through what we've done, then we've got a proof that those two models, and I like to tell my students, you're really an algebraic topologist if you equally love those two models for BZ, the simplicial model versus the S1. You know, that's when your heart is really that of an algebraic topologist somehow. Let me make a note then that because this is acyclic, that means that if I take the CW chains of this simplicial EG in any coefficient, this will be a resolution of R over the group ring RG. That's something that you need to start doing group homology, so a particular kind of homological algebra. So another thing we can say about all these spaces is, well, so G goes to BG is a very rich functor from groups to topological spaces. The functorality is immediate, so that's another nice thing. This is immediate by the simplicial construction, right? I can just apply the homomorphism to every element of the group, and then you can check that it respects the identities. So yeah, so this is a fun way you can, and I'll tell you more about this as I do some different examples of group homology. But let me go and start up where I should start at the top of the next column for the last bit I want to do, which is relate these to Eilenberg-MacLane spaces when we play this simplicial game. Good. So I'm geometrically minded. Why would I be such a fan of this? Let's see, question. What doesn't work here for indiscrete groups? So some of those things I was saying, I was ignoring the topology. You really, the definition I gave you for BG doesn't, oh, Andrew, you can make that comment to everybody. Go ahead and switch it. Yeah, and so go ahead and make your comment to everybody, Andrew, but right, and I meant to say in my notes, the nerve construction I really want to make as a topological simplicial set, i.e. a simplicial space, and then various statements that I made, you need to be working in that context. And I just didn't want to set up that much machinery, so I made itself easier. I made my life easier by just sticking to the discrete or finite setting. All of what I've said so far is absolutely true in case you want to account for the topology. And in fact, that's going to be key to the next set of examples. So yeah, here's what why I really love B delta G. Let me make a little proposition. that if G is abelian, let me actually call it A. Constructed with only discrete topology. Is it the case that the action of G on EG is constructed? So the action of G on EG. Well, let me get through this and then we can have a discussion. My apologies for moving on, but I'll come back to Peter's question at the end when I have time to think a little bit more. If A is abelian, and remember that's a topological group, then B delta A is also an abelian topological group. So what is the, this is almost a definition. So I've got my G1 and my G2, and then maybe I'll add it to something below. Right, if you want to use a nerve construction, I think we'd want to have topological categories and things sort of enriched somehow. Again, feel free to continue in the chat, people who might want to comment. But what is the group structure on these pictures? Well, that's what you might guess. We can just superimpose. So I started with 2 points and 3 points. I end up with 5 points, at least before I apply any identifications. But what if G2 and H3 were the same? So then these get H1, G1, H2. But then I'm going to use the fact that if these happen to be the same, which of course I need to account for, then I'm going to add. So, so this gives a group structure, and it's well defined. And here we really need, let me put the parenthetical comment into a different color. Here we need the abelian group. Otherwise, there's no way to continuously sort of make choices where you can imagine H3 starting slightly to the left or slightly to the right, or I said it reverse, but slightly to the left or right of G2, and sort of in the limit there would be some discontinuity in the multiplications, because you would have like H3 approaching G2 from the left, but then, oh, and my apologies, this is H3. You would have H3 approaching G2 from the left, but going to its product with G2 on the right. So that's fun. And of course, as mathematicians, we say, oh, great, I've got some endofunctor, I can apply it again. Well, maybe not all mathematicians talk like that, but in other words, we can make BBA. And this gets to the beginnings of, lots of constructions, lots of iterated loops and infinite stuff. But let's just focus on this a bit. The way I want to think about BBA, so let's just think about A as some kind of finitely generated. Think of it even as like just Z mod n or something like that. And BBA, then I'm taking times, and at every time I'm labeling it by an element of BA. So I've got A1 and A2, B1, or maybe I'll just call this A3, etc. And as these, I still have the identifications, both, I guess I should have had these as dashes, both on both ends. Well, let me just skip ahead and say this is homeomorphic to the space where I just take a square and I let elements of my group play in my square. And it's similar kind of grazing laws in this land. If these group elements, if these sheep run into each other, they have to add. And if they run off the any end, whether it be for the second B or the first B in this BBA, they vanish. So so then from what and let me just say an example, or yeah, if A is Z, this has a name, then Z is something that you could also think of as ZS2, the free abelian group on S2, which is based. This base point is sort of what everybody's vanishing to when they wander into at the boundary. So that's another way to think about this construction. But then the proposition that follows from before is that, well, so let A be, say, finitely generated abelian group. Then B in A is a K A. So for example, as I promised in the preview, you can put on your desks, as we are bound to our desks, a little model for KZ3, which is, people often think of as a mysterious space, but it sort of can sit in front of you. This is pretty immediate. This is why I chose to give the proof I did of uniqueness of BG. It followed also from this these exact sequences that showed you that the homotopy groups of G are just those of, sorry, the homotopy groups of BG are those, so this is, again, follows from the previous fact that we wrote down, that the I plus first homotopy group of BG is isomorphic to the ith homotopy group of G. And you have to have some care to get this off the ground. If A is like Z mod N, this is true. Pi 0 of A is given a group structure because A is a group, and that's Z mod N, and that's what pi 1 of B Z mod N is. And then after that, this is pretty immediate and easy. So this will be a perspective that I take later. It'll be a few lectures down, so later we'll talk about some geometry of Eilenberg-MacLane spaces, where this will be part of the discussion. The thing, as long as we're here and I'm mentioning this, let me tell you two important generalizations. And I'll come back to both of these, but, well, at least one of them. Suppose X is a finite complex, but then I embed it inside of some Rn or R infinity in and I take some neighborhood, so which is equivalent, which will then be this chunk of, this would be a manifold, a sort of trivial manifold, with manifold, trivial bundle, etc., framed manifold. Then I can, instead of the free abelian group, take integers with values of X, or, and again, other abelian groups. We could take what I might call it, for lack of a better thing, EX, which is the free the free object. Let's do this. Sorry. Take Sx, which is going to be the sort of free sphere spectrum object. But think of it as an infinite loop space way. So this is going to be a way. I'm sorry. I think I didn't do as well with that explanation as I'd like. But instead of little points of abelian groups roaming around in X and coming together and multiplying, if you have E infinity algebra, like the free infinity algebra, then you can let them collide and multiply, at least if you've got something embedded in R infinity. The other generalization is factorization homology. I might come back and say that more about that at some point, where if I've got a manifold M, then I can take, and these are elements of a A1, A2, I'll still call them, they're sort of abelian. They're abelian up to some amount of coherence depending on the dimension of M. And we can take a ENL algebra elements and let them run around in M. And the homotopy type is the factorization homology of M. Okay, that's about where I wanted to get to this time. Next time I'll talk about characteristic classes before doing more about Eilenberg-MacLane spaces another time. So what I'll do is first take questions with it still recording, and then if anybody has questions that they didn't want to share for posterity, I'll stop recording and we can take more questions.
I have a question.
Yeah. Hi, Andy.
Hi. So maybe I've forgotten this, but what if you take the non-path connected base, what do the free map homotopy classes of free maps into BG classify? There is an answer to that, isn't there?
Yeah, I mean,
I'm always a bit confused about this point, I must admit.
Right. I mean, I still, I mean,
maybe Jim Stashev knows.
Yeah, again, I don't, that's the kind of question that I need a moment to mull over. I mean, if you,
and more than a moment for me too.
Right. I mean, it's something I've seen statements about in the literature, but I've forgotten what the reason, what you actually get. It's a subtle distinction, I think.
Well, right. So one thing is, I mean, in the case of, I mean, there's some examples where freeing up the base point, you're really looking at, you know, like covering spaces up to conjugacy. So I kind of wonder.
I think that's the point, that you get sort of gauge transformations of the bundle.
Yeah, yeah.
Lurking around, and this is, I think, what always stuck in my mind, that there's some very subtle issue about this. I mean, I guess one point is that when you nail the base point, you're basically giving at a specific point a well-defined local trivialization at that one point.
Right, right.
And I guess if you don't insist on that, then
everybody
you
can
kind of, you know, you sort of, your local trivialization spreads out.
Yeah.
But if you don't pin it down at one point, it's freer somehow. But
right.
That's a little bit hand wavy, but I think there's something like that. But I don't know a place where this is really explained very well. Maybe somebody else knows? I mean,
if you think of the case of a bundle not principal with some arbitrary fiber, and when you classify the vibrations with that quote unquote fiber, What do you
Mhm.
mean? Do you mean that fiber is of a given homotopy type, or do you mean dead on? It has
Yeah.
the classification has to take that fiber to itself by the identity.
Right.
That's
Right.
one subtlety. I don't know if it answers your question.
Yeah, I mean, I think that's sort of consistent with what we were saying earlier, that you know, if you allow sort of different maps at the base point,
Right.
what you get different identifications of G, and that has to spread out as a principal G bundle. And so you get some sort of automorphism of the fiber.
Yep.
Right. But exactly what the precise statement is, I don't know. And I don't know a good place to find it in the standard literature. I'm sure it's there somewhere, but
and if people want, they can email me and I can post some of these things on the page, and that way anybody who checks the page can sort of go back and see, okay, this is where it addresses that point. I also wanted to say that this brings something to mind that I meant to say, but I think I passed over it, namely that these principal G bundles occur, you know, not only sort of in the group action context I emphasized, but also in fiber bundles anywhere of any sort, because the automorphisms of those come up, and the reason I elided over it a bit today is that I'll discuss that next week a bit more. There's a question in the proposition, I'm assuming it's that last proposition, that we get models for Eilenberg-MacLane spaces. Where do we need that A is finitely generated? I'm not sure. Again, that's where I have full confidence it's true in the argument that that I outlined, with the fact that these homotopy groups, right? If G is not, I would suspect maybe that first bit where going from pi naught of G, which is naturally a group via its group structure, to pi 1 of BG might be a little dicey if you're not finitely generated. It's probably true in more generality, but I didn't want to think about what you would really need to get going there. I think after that you would be okay, but that sort of pi naught of G is isomorphic to pi 1 of BG. I think there's some lifting and this and that that might be a little delicate, but I could be wrong there. It's more a lack of confidence on my part than knowing a counterexample that requires this hypothesis.
You can probably pass to colimits over. I mean, there's probably some argument that you can do it for finitely generated and then take colimits, but then of course the topology on a colimit of CW complexes can be a bit, I mean, it may not be what you want. So,
Great. Well, there's no further questions for public view. I'm going to stop sharing. I will not stop the thing yet in case anybody had any questions that they wanted for just a smaller consideration.
Thanks again, Deb.
Yeah.
No, you're very welcome. You're very welcome.